Hello and welcome back to the video lessons for outcome 30.6. Today we are going to start looking at what a permutation is. So on our rubric, we are going to be able to solve basic permutation questions when I'm told what type. And I'm going to be able to solve some permutation questions. In this case, I'm looking at ones with conditions at a level 3. So now, again, let's go over that goal. Our goal is to look at something called a permutation, which is something that we already discussed in the previous lesson. So whenever we look at permutations, remember, that's when we remember order matters. So I want to arrange the letters in the word task into 2-letter combinations. That means that my order is important. If I scroll this down, you get to see all those different options. You have TA and AT because they are different permutations. Order matters. TS, ST, TK, KT, AS, SA, so on and so forth. Those are all your different options. Because, again, the order matters. Now, as you get more and more objects, it becomes tedious to list them all like this. So, what we have is a formula for permutations. So, a permutation, if you look, you should have a button that looks just like this on your calculator. The N stands for how many options you have, and R stands for how many of those options that you want. The formula then is n factorial over n minus r factorial. For most instances, you're going to be happy just using the button on your calculator. This formula will pop up on sometimes level 4 type questions, where you have to reduce factorials like we did in lesson 2. So if I look at that previous question, if I use this permutation formula, we had the letters in task, which means there was 4 of them. I wanted to pick 2 of them. And if you punch that in, you do end up with 12 different ways. So again, the NPR is notation commonly represent permutations. You always want to put the number of options first, and then, the number of total options first, and the number of options that you want second. The bigger number should always be first, smaller number should always be second. If you use all the options, then it's like NPN, and that is okay. So, let's carry on. Let's try something. So it says, how many 3-letter permutations? So right away, it tells me I'm finding permutations. I'm going to use the P button. Using the letters in the word compute. 1, 2, 3, 4, 5, 6, 7 total letters. I need to pick 3. You simply punch that into your calculator, and you get 210. The next one says, from a group of 100 people, how many ways can a president, vice president, and treasurer be selected? Well, the order matters. Being president is different than being vice president, which is different than being the treasurer. So order matters. When order matters, I use a permutation. I have 100 people to pick from. I need to pick just 3. So how many ways can we do this? 970,200 different ways. Three says a coach must choose 3 out of 10 players for a tie-breaking penalty shot. The coach must designate the order. So he has to designate the order. Order matters. That's a permutation. I have 10 players to pick from. I need to pick 3. 10p3 is 720. So again, when order matters, you are more than welcome to use that permutation button on your calculator. Next example says Matt has downloaded 10 new songs. He wants to create a playlist of 6, arranged in any order. So that means that the order is going to matter. When order matters, I do a permutation. So I have 10 songs. I need to pick 6 where order matters. 10p6 is 151,200. Now I'd like to draw your attention to the fact that whenever order matters, you are more than welcome to use the fundamental counting principle. So another option is to do your blanks. You have 6 tasks, 6 songs. You have 10 songs for the first option, then 9, then 8, then 7, then 6, then 5. And if you multiply through, you get the exact same answer. You choose which one you like better. They're both going to get you to the right spot. Let's try another example. In how many ways can I arrange all the letters of the word oranges? So 1, 2, 3, 4, 5, 6, 7. There's 7 letters there. If there's no restrictions. So if there's no restrictions, that means I just arrange them all. I have 7 letters. I need to pick all 7. And again, I want to draw the attention to the fact that I could also make 7 blanks and have 7 options for the first, then 6, then 5, then 4, then 3, then 2, then 1. That dot, again, just means multiply, which in this case, it starts at 7, goes all the way down to 1, is 7 factorial. All 3 of those would get you the right answer of 5,040. Now, whenever you have restrictions, like in B, where it says the first term has to be an N, I typically always use the fundamental counting principle. 3, 4, 5, 6, 7 blanks. And you always start with the restriction first. Always, always, always. So my restriction in this case is that it has to start with an N. This one has to be an N. If it has to be an N, it has to be an N. There's only one option for it. Leaving me 6 options for the next, then 5, then 4, then 3, then 2, then 1. And so for that one, I get 720 different ways. C is another restriction, and it's by far the hardest restriction on this example. It says that the vowels O, A, and E have to be together in that order. So right away, as soon as I see that there's restrictions, I start with my fundamental counting principle. 7. And it tells me that the O, then the A, then the E have to go together. It doesn't tell me where in that lineup they need to go, so I always start with them going first. So that means there's only one option for the O, one for the A, and one for the E. That leaves me with 4 letters, 4 options here, 3 options here, 2 options here, and 1 option here, and I do too many blanks. So I'm going to get rid of it. There should only be 7. And so if I multiply 1 times 1 times 1 times 4 times 3 times 2 times 1, I get 24 different ways. But like I alluded to earlier, the O and the A and the E didn't have to be the first 3, right? So I put them in the first 3 spot here, but they didn't have to be. They could have went here. That's my second option. They could have went here. That's my third option. They could have went here. That's my 4th option. And they could have went here, which is my 5th option. So I have to take that answer and multiply it by 5, because there's 5 different places that the O and the A and the E could go, giving me a grand total of 120 different ways. One more example of a permutation, and we're going to look at Syn numbers. So your social insurance number is a 9-digit number, the digits 0 to 9. On the side note, never tell anybody your Syn number. That number represents you to the government. If there are no restrictions whatsoever, I can repeat. Let's figure out how many different ones I can have. So again, I just like fundamental counting principle. I'm going to make 9 blanks. 4, 5, 6, 7, 8, 9. If I'm using the digit 0 to 9, it means I have 10 options. So I have 10 options for the first, 10 for the second, 10 for the third. I actually have 10 for every single option if there's no restrictions. And I multiply that through, and I get 1 billion. There is 1 billion different ways I can make a social insurance number. Now, in the second part of this question, it says, how does that compare with the total number of Sims if if I'm not allowed repetitions, if I'm not allowed to repeat. So again, I make my 9 blanks. 1, 2, 3, 4, 5, 6, 7, 8, 9. I still have 10 options for the first number, but now I'm not allowed to repeat it. Only got 9 left, then I would only have 8, so on and so forth, until I run out of blanks. And again, I multiply all the way through, and I end up with now only 3,628,800 different options. So anytime where there's a permutation and there's no objects that are identical, you are more than welcome to use the fundamental counting principle. It is now time to try practice number 3.